Usually, when you get a medical diagnosis, there's this fundamental expectation of absolute binary precision.
Oh, wait, absolutely. Yeah.
It feels almost like structural engineering. You know, if you break your arm, you go into a room, the X-ray machine spins up, and it captures that jagged, brilliant white line across the bone.
Right. You can literally see it.
Exactly. The doctor just points to the illuminated screen and tells you there's the fracture, it's visible, it's measurable, it's just a clean, definitive reality.
And, I mean, we find deep psychological comfort in that kind of visibility. When a system is deterministic like that, we can categorize it. We can isolate the variables, and we can map a direct linear path to a solution.
But the moment you step outside of that sterile hospital room, the moment you step into the world of predicting the future state of our chaotic, turbulent atmosphere, that pristine X-ray machine just shatters.
It really does. It's a completely different ballgame.
Yeah, the diagnostic landscape we are forced to look at is fundamentally murky. The Earth's atmosphere is this chaotic fluid, constantly churning, constantly exchanging heat and moisture across thousands of miles.
Right.
And today, we are looking at the most massive disruptive technological leap in the history of trying to diagnose that murky landscape. We are talking about artificial intelligence taking over weather prediction.
Honestly, it's a paradigm shift that is rewriting the foundational laws of how we generate a forecast. We are basically witnessing the death of one era and the rapid, almost violent birth of another.
And the central fascinating paradox of the Meteorology Matters podcast today is that, well, while this predictive technology is experiencing an absolute golden age, the physical foundation of public weather safety is quietly crumbling beneath it.
That's the real tension here.
Right. We are trying to show how two very contradictory things can be true at once. AI may be making hurricane forecast models faster, sharper, and in many cases significantly more accurate, but, and this is key, that does not mean the overall forecasting system is automatically stronger.
Not at all, because those AI models, they still depend entirely on physical observations.
Exactly.
I mean, satellites, weather balloons, aircraft data, ocean sensors, massive research labs, and of course, experienced human meteorologists to actually interpret the guidance and communicate the risk to you.
Yeah, you simply cannot separate the brilliant high-speed algorithms from the physical, grounded reality of how we gather the data to feed them.
You really can't.
So, heading into this hurricane season, we face this incredible tension. We have the best forecast tools ever conceived by human minds on one side, while staffing cuts, research lab closures, and reduced global observations actively weaken the system surrounding those tools on the other.
It's the systemic paradox of our time. We are building the smartest engines in history, but we are slowly turning off the fuel supply.
That specific tension is what will define how forecasts perform this season. But before we get into the deep mechanics of all this, I want to take a brief moment for some housekeeping.
Sounds good.
If you want to follow the latest updates, follow meteorologist Rob Jones on Instagram @meteorologist, on TikTok @tvmeteorologist, and on YouTube by following Rob Jones Hurricane, where you can also find the Meteorology Matters podcast playlist.
Definitely go check those out.
And please take a second to like, follow, comment, and rate the podcast.
It genuinely helps elevate the science we're trying to share.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones. Now, let's get into today's episode of Meteorology Matters.
I am thrilled to be here.
I am so glad you're in the studio today to help us unpack the extensive research that has been done on this collision between cutting-edge digital infrastructure and raw, chaotic nature.
It is a privilege to be here. We are standing at an inflection point that is going to fundamentally alter how society interacts with and prepares for the Earth's atmosphere.
To truly grasp the magnitude of the AI revolution, I feel like we have to establish a firm baseline of what it's actively replacing.
Right. Context is everything.
So, for the last several decades, the old guard of forecasting has been numerical weather prediction. Can you walk us through the mechanics of that traditional system? How have we historically forced a supercomputer to tell us if it is going to rain next Tuesday?
Well, for over half a century, forecasting the weather has been an exercise in brute force physics.
Brute force?
Yeah, literally. To make a computer understand the atmosphere, you have to build a digital version of the Earth. Imagine taking the entire globe and wrapping it in a massive, invisible, three-dimensional mesh grid.
Okay, I'm picturing that.
You are slicing the atmosphere into millions of tiny interconnected cubes,
Yeah.
stacking them from the surface of the ocean all the way up into the stratosphere.
Wait, so we are building a literal wireframe cage around the planet, and every single intersection of that cage holds a specific volume of air.
That is the architecture exactly. Traditional numerical weather prediction takes the current, real-time state of the atmosphere, the specific temperature, the relative humidity, the barometric pressure, the horizontal and vertical wind speeds, and it injects those initial observations into every single one of those millions of tiny cubes.
That sounds like an insane amount of data.
Oh, it is. And once that initial state is lost into the grid, the supercomputer begins its heavy lifting. It has to solve a set of deeply complex mathematical formulas known as the Navier-Stokes equations for every single box.
Okay, the Navier-Stokes equations. Those are essentially the holy grail of fluid dynamics. They are the mathematical bedrock that describes exactly how viscous fluids move.
They are. The supercomputer is actively enforcing the strict, immutable physical laws of the universe. The conservation of mass, the conservation of momentum, and the conservation of energy.
So it's calculating everything.
Everything. It is calculating, based purely on thermodynamics, exactly how the heat and moisture currently sitting in box A will physically flow into and alter the state of box B over the next 5 minutes.
Wow.
Then it calculates the next 5 minutes, and the next. It marches forward in time, forcing the atmosphere to obey the laws of physics, projecting days into the future.
I want to use an analogy here to ground this concept for you listening. Traditional forecasting feels essentially like trying to calculate the exact rigid physics of every single bounce in a chaotic pinball machine.
Oh, that's a great way to put it.
Right. Like, to predict where the ball is going, you are forcing a computer to mathematically measure the angular velocity of the flipper, the specific friction coefficient of the polished wood, the elastic tension of the bumpers, and the exact mass of the steel ball.
Exactly.
You are trying to rigidly calculate every physical variable as it happens in real time.
That analogy holds up perfectly because it illustrates the computational exhaustion involved. The atmosphere is not a static environment. It is a continuously flowing, highly turbulent, deeply nonlinear fluid.
Right.
Running those rigid calculations takes a staggering toll on our hardware. We are utilizing warehouse-sized supercomputers, drawing massive amounts of electricity, running quadrillions of calculations per second.
And it still takes a while, doesn't it?
Yes,
Mm-hmm.
even with all that silicon power, it takes these machines several hours just to run a single global forecast.
Hours.
And the truly frustrating part is that despite all that heavy math, these models still suffer from a systemic flaw known as the parameterization problem.
Let's isolate that flaw, the parameterization problem. This has to do with the physical size of those wireframe grid boxes we built, doesn't it?
It does.
Because even in our most advanced multi-million-dollar global models, a single grid box might be 6 to 10 miles wide.
Right.
But a violent, localized thunderstorm or a specific, concentrated updraft inside the eye wall of a major hurricane, that feature might only be 1 mile wide.
Exactly. And if the physical weather event is smaller than the digital box containing it, the supercomputer literally cannot see it.
So it just misses it.
It becomes a subgrid scale process. You have identified the absolute ceiling of traditional forecasting. The computer is blind to anything smaller than its own grid resolution.
That seems like a massive blind spot.
It is. So, to prevent the entire global model from crashing or ignoring localized convection entirely, physicists are forced to write separate, highly simplified algorithms to essentially guess what the small-scale weather is doing inside the larger box.
And that guessing is the parameterization.
Yes, that is parameterization. It is a mathematical estimation meant to simulate complex subgrid physics. And because it is an estimation, it is incredibly prone to systemic errors.
Like what kind of errors?
Well, the model might systematically overforecast rain in the tropics or underforecast the rapid intensification of a hurricane simply because the underlying grid is too coarse to resolve the true physics of the storm's core.
Which brings us to the new frontier. Based on the research that's been done, artificial intelligence is arriving and completely upending this brute force paradigm.
Completely.
The AI doesn't just improve the Navier-Stokes equations, does it? It discards them entirely.
The transition here is difficult to overstate. The AI models bypass the rigid physics completely.
Wait, completely.
Completely. They do not calculate the conservation of momentum during the forecast. Instead, the massive computational burden is shifted away from the real-time forecast window and placed entirely onto the historical training phase.
Skipping the physics feels almost like cheating the system. But the underlying methodology is fascinating. How does a neural network predict the weather if it doesn't understand the laws of thermodynamics?
It relies on deep learning and a vast resource known as reanalysis data.
Reanalysis data, what is that?
Reanalysis is a massive, meticulously balanced, mathematically complete archive of historical global weather data, usually spanning the last 40 to 50 years. The researchers feed this massive archive into the neural network. The AI model looks at the complete global atmospheric state on a Tuesday in, say, 1994. It analyzes the billions of data points. And then it looks at the verified historical reality of what actually happened on Wednesday in 1994.
Ah, it is essentially looking at the initial state of the board and then immediately looking at the answer key.
Millions upon millions of times. Through deep learning matrices, the network intuitively adjusts its internal weights to learn the highly complex nonlinear patterns connecting the state of Tuesday to the state of Wednesday.
So it isn't doing the math.
No, it does not know what a fluid is. It does not know that warm air rises.
That is wild.
It simply recognizes that when the global atmosphere presents a highly specific, multidimensional pattern of temperature and pressure, it almost always resolves into this subsequent pattern 24 hours later.
Returning to our pinball analogy, the AI is no longer the physicist with a clipboard trying to measure the friction of the wood and the velocity of the flipper.
Right.
The AI is simply a seasoned arcade veteran who has stood in the corner of the room and watched a million consecutive games of pinball.
That's exactly it.
The veteran doesn't know the mathematical formulas for elastic collision, but because they have seen the pattern so many times, they intuitively know exactly where the ball is going to end up the second it leaves the plunger.
The AI operates purely on highly evolved pattern recognition. And because it does not have to pause and calculate the rigid physical laws of fluid dynamics in real time, because it simply looks at the current data and instantaneously recognizes the pattern, the speed at which it can output a forecast is genuinely staggering.
It's a revolutionary leap in efficiency.
It really is.
But skipping the physics isn't just a neat parlor trick, is it? It fundamentally changes the mathematical equation of survival.
How so?
Well, when you remove the Navier-Stokes calculations, you buy back time. And time lets you run probabilities.
Ah, yes. Probabilistic forecasting.
The metrics highlighted in the research that has been done are hard to even wrap your head around. We are looking at deep learning models like GraphCast and GenCast.
Yes, the big ones.
These AI systems are generating high-resolution, 15-day global forecasts in roughly 8 minutes on a single desktop computer chip.
It's unbelievable.
And they are consistently outperforming our multi-million-dollar deterministic physics models on over 90% of the standard verification targets.
And speed on that scale equals safety because it unlocks the true potential of probabilistic forecasting.
Explain that for us.
With a traditional slow physics model, you are severely bottlenecked by supercomputer time. You can only afford to run the global forecast maybe 50 times simultaneously, with slight variations in the starting data.
We call that an ensemble.
Right. 50 runs gives you a decent functional idea of the middle of the bell curve, most likely outcome of a storm's path. But weather is intrinsically chaotic.
Very chaotic.
A microscopic shift in initial wind speed or moisture content can compound over several days and push a developing storm into a catastrophic edge case scenario.
Like a major hurricane suddenly deviating from the consensus track, hooking sharply to the left, and stalling directly over a densely populated metropolitan area.
Those are the nightmare scenarios. We call those edge cases the tails of the bell curve. Because the AI is so incredibly fast and computationally cheap to run, you are no longer limited to 50 ensemble members.
You can run it a lot more.
You can run the AI model 1,000 times or 10,000 times almost instantly. You introduce microscopic, localized perturbations to the starting data for each run. By doing this, you illuminate the entire probability space.
You can clearly see those low-probability, high-impact tail events forming in the data.
Exactly. And you can communicate that precise, quantifiable risk to emergency managers a week in advance.
The research that has been done highlights real-world triumphs from the 2025 hurricane season, where this probabilistic power materialized in real time.
Yes, it was a very telling season.
I want to examine the divergent behaviors of the traditional models and the AI models during Hurricane Lee and Hurricane Melissa. What specifically did the artificial intelligence recognize that the physics models missed?
Well, Hurricane Lee was a masterclass in providing actionable lead time. The AI model successfully locked in the precise ultimate track for Hurricane Lee 9 full days before landfall.
9 days! That's incredible!
Traditional physics models, bogged down by complex steering currents and shifting high-pressure ridges, struggled with the parameterization of the environment. They did not converge on the correct track until roughly day 6.
3 extra days. In the realm of coastal emergency management, 3 days is an absolute eternity.
It is the difference between life and death.
That is the physical difference between safely staging ambulances and evacuating a massive coastal hospital system versus widespread panic and gridlock on the interstate highways.
It alters the entire paradigm of civic disaster response. You are moving from a reactive posture to a proactive, highly coordinated strategy.
And the AI's performance during Hurricane Melissa was perhaps even more impressive, wasn't it?
It was, because Melissa was a late-season storm. Late-season development is notoriously difficult for traditional models to resolve.
Because the background state of the atmosphere is undergoing a massive seasonal shift.
Right.
You have the residual deep summer heat stored in the oceans clashing violently with early fall-like baroclinic cold fronts plunging down off the North American continent.
And the energy transfers during a baroclinic transition are incredibly chaotic. A tropical cyclone draws energy from latent heat release over the ocean, while a cold front draws energy from horizontal temperature gradients.
So they clash.
When those two systems interact, the traditional physics models often struggle to calculate the energy exchange accurately. But the AI, drawing on its vast database of historical reanalysis, recognized the deeply complex transition patterns immediately.
Just from pattern recognition alone.
Yes. It resolved the interaction with such early consistency that it gave the human forecasters at the National Hurricane Center the statistical confidence to explicitly predict a Category 5 landfall days in advance.
Predicting a Category 5 landfall explicitly on an official forecast cone is a massive, highly scrutinized operational decision.
It really is.
It triggers billions of dollars in economic movement. You do not make that call unless you trust the tools in front of you implicitly.
And this is where we have to be careful. This reliance on deep learning introduces a profound structural vulnerability into the science. And this is the critical turn in our discussion today. The AI is dominant in speed and pattern recognition, but it achieves that dominance by sacrificing transparency.
If the AI is so fast and its skill scores are dominating the charts, it raises an obvious question for you listening. Why don't we just unplug the warehouse-sized supercomputers, save millions in electricity, and let the AI run the National Weather Enterprise?
A fair question.
If you are trusting these forecasts to protect your family, you might be asking if we are risking public safety by blindly handing the keys over to a digital black box.
The black box problem is the exact term the meteorological community uses, and it is the single greatest hesitation regarding AI implementation.
Walk us through that.
If a traditional deterministic physics model gets a forecast completely wrong, let's say it hallucinates a hurricane in the Atlantic that never actually forms, our research scientists can open up the code. They can trace the calculations step by step and locate the exact heat flux equation or the specific parameterization scheme that derailed the model.
So you can see the math.
We can see the math. We can identify the failure point, adjust the physics, and prevent it from happening again.
The mechanics are transparent.
Exactly.
Yeah.
But with a neural network, you don't have equations. You just have a matrix of a billion adjusted weights.
Right.
If the deep learning model hallucinates a hurricane, we know it recognized the wrong historical pattern, but we have absolutely no idea why it triggered that specific pattern.
It's just a black box.
The internal logic of the network is so mathematically complex and layered that it is largely uninterpretable to a human mind.
We cannot trace the error.
We can't. And you cannot automate life safety decisions based on an uninterpretable algorithm.
That makes total sense.
This is why the experienced human forecaster is actually more vital now than ever before. The AI is a brilliant synthesizer of massive data sets, but human experts must act as the critical filter.
They have to interpret the AI guidance?
Yes, they have to recognize the historical biases inherent in the training data, compare the AI output against the traditional physics models, and ultimately communicate a coherent, contextualized narrative of risk to the public.
It is not about replacing the physics. It is about merging the two paradigms.
Exactly.
The research that has been done points to a brilliant hybrid solution currently deployed in the Gulf of Mexico involving coastal engineering and storm surge modeling.
Oh, this is a fantastic example.
Just beautifully illustrates how uninterpretable machine learning can actually fix the systemic flaws of rigid physics.
It is a stunning example of operational synergy. Let's examine traditional storm surge models, specifically a program like ADCRC.
ADCRC.
Okay. This is a hardcore traditional physics model. It meticulously calculates the physical stress of the hurricane-force winds pushing on the ocean surface, the inverse barometer effect where low pressure allows the ocean to physically bulge upward, and the complex wave setup as swells approach the coast.
But ADCRC is still bound by the same structural limitations we discussed earlier.
It is forced to calculate those forces on a predetermined grid. And if you are mapping the incredibly complex coastal environment of the Gulf of Mexico, a 6-mile grid is entirely insufficient.
Because a coarse physics grid cannot see a localized sandbar.
Exactly. It cannot resolve a narrow meandering inlet or the specific topography of an inland estuary.
And because it is blind to the microgeography, the physics model makes systemic, highly repetitive errors.
Spot on. For example, the ADCRC model might systematically underestimate the peak water level inside a specific localized bay by exactly 2 feet every single time a storm approaches from the southeast quadrant.
Why does it do that?
It makes this error because its coarse grid simply cannot see the narrow inlet that actively funnels and compresses the incoming water.
So it makes the exact same mathematical mistake over and over again because the physics are rigid.
Now, instead of throwing out the multi-million-dollar physics model or spending decades trying to build a finer grid that would crash the supercomputers, researchers trained a highly specific type of AI.
What kind of AI?
They built an LSTM, or long short-term memory neural network, to act as a localized intelligent post-processing filter.
An LSTM filter. How does that network interact with the flawed output of the physics model?
They trained this specific LSTM network on the highly localized, verified tide gauge data from just 6 diverse historical storms that impacted that specific bay.
Just 6 storms.
Yes. The AI essentially looks at the flawed historical output of the physics model, compares it directly to the verified reality of the physical tide gauges, and learns the systemic bias. It effectively grades the physics model's homework.
Oh, wow. So in real-time operations during an approaching hurricane, you run the fast, computationally efficient physics model to get your baseline regional surge.
Right.
Then you feed that baseline output directly through the AI filter. The AI instantly corrects the geographic bias.
Exactly. It recognizes the physics model is projecting 5 feet of surge for this bay, but based on the historical pattern of this specific wind angle, I know the physics model always underrepresents the funneling effect of the inlet. The true localized threat is actually 7 feet.
It is an elegant fusion. You are utilizing the immutable laws of fluid dynamics to generate the macro environment and then deploying the adaptive, localized pattern recognition of machine learning to correct the micro flaws.
That's the perfect way to summarize it.
We have established that we possess this brilliant new AI processor, and we have hybrid models fixing rigid physics errors. But here is where we hit the foundational paradox that defines this episode.
The big paradox.
As the research that has been done so clearly outlines, a brilliant digital processor is utterly, completely useless without a steady stream of raw data pixels feeding into it.
The observation foundation.
Yeah.
This is the absolute bedrock of all meteorological science, and it is currently undergoing severe systemic decay.
Severe decay.
An AI model, no matter how vast its historical training data, does not magically know what the weather is doing over the Pacific Ocean right now. It relies entirely on real-time observations to initialize its current forecast.
Right. If you do not provide the AI with a highly accurate starting point, the pattern recognition fails instantly.
It's garbage in, garbage out.
The processor needs the feed. It needs the network of low Earth orbit satellites, the coastal Doppler radars, the Hurricane Hunter aircraft reconnaissance, and the daily weather balloon launches.
It needs all of it.
But having the sensors is only half the battle. We have to discuss the vital, incredibly complex science of data assimilation. Let's dispel a common myth here. A weather satellite floating in the vacuum of space is not just pointing a high-resolution camera at the Earth and taking a picture of a thermometer.
That is a critical misconception. Satellites do not measure temperature directly.
What do they measure?
They measure microscopic, highly specific variations in microwave and infrared radiation bouncing off atmospheric molecules, primarily oxygen and water vapor at various altitudes.
So it is just raw numeric radiance data streaming down from space.
Yes, and highly specialized research scientists have to build brutally complex, mathematically dense translation algorithms to convert that specific radiance reading into an actual temperature value.
That sounds intense.
It is. Then they have to slot that newly calculated temperature into the exact, correct three-dimensional location in the model's initialization grid without breaking the surrounding mathematical code or introducing artificial shock waves into the model.
And that entire grueling process is data assimilation.
Exactly. If you do not have dedicated scientists actively writing and updating that translation code, the raw satellite data remains completely unreadable to both the AI and the physics models.
Which brings us to the structural shifts occurring within the government right now. And I want to frame this carefully for you listening.
Yes, we need to look at the numbers.
Based purely on the research that has been done. We are looking objectively at the numbers proposed in the upcoming 2027 federal budget. We are strictly impartial here, not taking any political sides, just examining how those shifts directly impact the mechanical machinery of weather prediction.
The numbers represent a profound structural recalibration of how the nation prioritizes and funds the acquisition of scientific knowledge.
The proposal outlines a massive 40% increase in defense spending. To fund that rapid pivot toward immediate operational security, the budget proposes historic, sweeping cuts to basic science and environmental research across the board.
Massive cuts.
The National Science Foundation is facing a proposed 55% cut. The EPA is facing a 52% reduction. NASA science programs are facing a 47% cut.
It's sweeping.
And zooming in on our specific infrastructure, NOAA, the National Oceanic and Atmospheric Administration, is facing a 28% cut to its operating budget.
But the most critical detail buried within those numbers, the detail that directly impacts everything we have discussed today, is that the proposal completely eliminates the Office of Oceanic and Atmospheric Research. OAR.
The elimination of OAR. Now, if you were living on the Gulf Coast right now or in a flood zone in the Northeast, you might be looking at your phone and thinking, my weather app works perfectly fine today, the daily forecasts are highly accurate. Why do I care if some bureaucratic research office in Washington is closed?
A lot of people probably think exactly that.
Let me offer an analogy to explain why this specific closure is so dangerous. It is essentially like going out and buying a state-of-the-art 8K resolution smart television. That represents the new AI models. But deciding to permanently fire the technicians who upgrade the cables, leaving you with only a dusty VHS player to plug into it. The screen is brilliantly capable, but the data feed you are providing it is obsolete.
That captures the dynamic perfectly. Modern weather forecasting is not a static achievement. It is a continuously evolving infrastructure.
Yeah, right.
We are constantly designing and launching new, highly advanced satellites that operate on entirely new frequencies, outputting massive new streams of complex radiance data. OAR is the research and development engine of the weather enterprise.
They are the scientists who study rapid hurricane intensification.
And crucially, they are the scientists who build the data assimilation algorithms.
So if OAR is eliminated, the continuous research into data assimilation simply stops.
It stops. We will have billions of dollars of cutting-edge satellites orbiting the Earth, generating vast, unprecedented amounts of critical data about incoming atmospheric rivers or developing tropical cyclones.
But our AI models and our physics models will become completely blind to them.
Exactly. The operational computers will not know how to ingest or read the new microwave telemetry. Our predictive capabilities will rapidly stagnate, trapped by old algorithms, while the global climate simultaneously grows more volatile and complex.
And this decay of the observational infrastructure is not some theoretical, localized problem projected for a decade from now. It is actively happening in real time.
It is happening right now.
Let's look at the sudden systemic shock of the DMSP blackout highlighted in the research that has been done.
The Defense Meteorological Satellite Program. This was an abrupt, highly disruptive halt to a critical stream of observational data.
What specifically did the DMSP satellites provide to the meteorological community?
The DMSP constellation provided extremely high resolution, specialized microwave imagery of cloud structures, atmospheric moisture profiles, and polar sea ice concentration passing over the globe twice a day.
And that's different from normal satellite imagery, right?
Very different. Unlike visible satellite imagery, which is useless at night or obscured by upper-level cirrus clouds, Microwave imagers can essentially see through the top layer of the storm.
Oh, wow.
Hurricane researchers relied heavily on this specific microwave data to peer deep into the internal convective structure of a developing tropical cyclone, locating the precise center of circulation before an eye even forms.
So you lose that microwave imager, and you fundamentally lose the ability to see the internal heat engine of the storm.
The data collection and distribution was abruptly terminated. Leading hurricane researchers explicitly stated in the documentation that losing this data leaves them operating blind to the complex inner workings of developing storms far out over the open ocean.
That is terrifying.
It is a sudden, massive loss of situational awareness that degrades our ability to initialize the AI models accurately, effectively setting localized forecasting back by decades.
And the decay extends beyond orbital assets. We are seeing severe degradation on the ground level as well. The research that has been done points to a highly concerning service change notice issued in April 2025 by the National Weather Service.
Ah, yes. The suspension of the radiosonde network, the weather balloons.
The notice explicitly stated that due to critical staffing limitations, severe budget constraints, and shifting operational priorities, the National Weather Service is temporarily reducing or entirely suspending scheduled weather balloon launches at selected critical sites across the country.
This is a devastating blow to the initialization phase of both physics models and artificial intelligence.
Why are the balloons so important if we have satellites?
Satellites are incredible tools, but they scan the atmosphere from the top down, inferring layers based on radiation. Radiosondes are physical instrument packages that physically float up through the entire troposphere and into the stratosphere.
So they get direct measurements.
Yes, they provide vital, high-fidelity, direct physical measurements, the absolute ground truth of temperature, dew point, and wind speed at every single pressure level. They provide the actual vertical slice of the atmosphere from the ground up.
And the deep learning matrices of the AI models mathematically require those precise vertical profiles to understand the three-dimensional shear environment, right?
Absolutely. If you starve the AI of high-resolution vertical observation data, its pattern recognition instantly degrades. It cannot accurately forecast the multidimensional evolution of a storm if it cannot clearly see the vertical structure of the atmosphere it is starting from.
If we connect this localized infrastructure decay to the broader global picture, the research that has been done strongly emphasizes that artificial intelligence already struggles heavily in regions of the world that lack dense observational data.
The inequity of global observation is a profound crisis.
The research specifically highlights the African continent as a tragic, ongoing example of this data void. Africa suffers the highest per capita fatalities from lightning strikes in the entire world.
The storms there are incredibly intense.
The Congo Basin experiences some of the most incredibly violent, highly electrified convective thunderstorms on the planet. Yet, vast swaths of the continent completely lack the dense, ground-based Doppler radar networks and physical sensor arrays that we take for granted in North America and Europe.
And because the physical data simply doesn't exist, the AI cannot accurately predict the localized severity of the lightning or the flash flooding there.
It has no high-resolution historical data to learn the patterns from.
Precisely. The AI is a mirror. It is only as good as the physical sensor network beneath it.
Right.
If the United States actively chooses to defund and degrade its own domestic observation networks, if we intentionally stop launching weather balloons, shut down critical satellite telemetry feeds, and eliminate the research labs that process the data, we will artificially introduce those exact same perilous blind spots over our own sovereign soil.
We are actively degrading the very pixels that make the multi-million-dollar AI processor valuable in the first place. And the timing of this physical infrastructure decay could not possibly be worse, because the atmosphere is currently throwing increasingly complex, thermodynamically unprecedented curveballs at us.
Curveballs that the AI has likely never seen in its 1994 training data.
Let's examine the underlying thermodynamics for the upcoming hurricane season. What is the massive conflicting tug-of-war happening over the oceans right now?
The research that has been done highlights a deeply conflicting, highly volatile signal driven by an accelerating climate system. We are essentially watching a heavyweight battle between a metric called potential intensity and an opposing atmospheric force known as the moist entropy deficit.
Let's break down the mechanics of those two forces. What is potential intensity in a physical sense?
You have to view a hurricane not just as a storm, but as a massive natural Carnot heat engine. It actively extracts thermal energy from the warm ocean surface, transports it upward through deep convection, and converts that heat into kinetic wind energy.
Okay, a heat engine.
Potential intensity is the strict thermodynamic calculation of the absolute maximum wind speed a storm could theoretically achieve in a given environment, based purely on the temperature differential between the hot ocean surface and the cold upper atmosphere.
And right now, the global oceans, particularly the deep main development regions, are hotter than we have ever recorded.
The ocean heat content is staggering.
It is acting like a massive, fully charged lithium-ion battery just waiting for a spark.
The potential intensity values are physically off the charts.
Right.
The oceanic environment is primed for explosive, violently rapid intensification.
There is a massive opposing force currently dominating the atmospheric circulation, the moist entropy deficit.
Yes.
How does that deficit physically inhibit the storm?
The deficit is a metric of how exceptionally dry the middle layer of the troposphere is currently running. And under current highly anomalous climate patterns, while the ocean surface is boiling hot, the mid-levels of the atmosphere are becoming exceptionally hostilely dry.
And dry air is utterly toxic to the development of a hurricane.
Because it disrupts the heat engine. Exactly.
How does it do that?
If that dry mid-level air gets pulled or entrained into the outer circulation of a developing tropical wave, it causes the moisture inside the clouds to rapidly evaporate. Evaporation is a cooling process.
Right, like sweat cooling you down.
Exactly. This creates dense, cold, heavy downdrafts that physically crash down to the ocean surface, choking off the vital inflow of warm, moist air into the storm's core.
So it actively kills the thermodynamic engine before it can start spinning.
It does. So we have incredibly hot oceans screaming for violent storm formation, and a highly dry mid-atmosphere actively fighting to suppress and tear apart any convection that tries to organize.
It is a massive thermodynamic tug-of-war on a global scale, which makes forecasting the seasonal statistics for this year incredibly fragile.
Very fragile.
If you live in a coastal zone, perhaps along the Gulf of Mexico or the eastern seaboard, and you watch a seasonal forecast update that says, "We expect a significantly below-average hurricane season because there is a massive amount of dry air or disruptive wind shear," can you relax? Can you skip buying the plywood and the hurricane shutters this year?
A firm, unequivocal, absolute no. Believing that a suppressed seasonal average equates to localized safety is the single most dangerous illusion in meteorology.
Because it only takes one.
Because a suppressed atmospheric pattern overall does not equate to a zero-risk season locally. The broad atmospheric pattern might be highly hostile to tropical development for 90% of the summer, but the atmosphere is a chaotic fluid.
It constantly ebbs and flows.
Yes. If that suppressive wind shear relaxes or that dry air mass temporarily moves away for just one single week in late August, and the atmospheric alignment moves perfectly over those incredibly hot, fully charged waters in the Gulf of Mexico, a storm will form.
And with that much available potential intensity, it will explosively intensify.
Without a doubt.
The classic, devastating historical precedent for this exact scenario is the 1992 season.
1992 is the ultimate cautionary tale.
It was a notoriously quiet, significantly below-average hurricane season, driven by an El Niño pattern that suppressed activity across the basin.
Most of the summer was perfectly, blissfully calm. But during one brief, isolated window where the shear relaxed, that quiet season produced Hurricane Andrew.
A storm that rapidly intensified and leveled South Florida as a catastrophic, tightly wound Category 5 hurricane.
Exactly. So global statistical averages offer you absolutely zero physical protection if the one singular major storm of the year decides to track directly over your living room.
You must prepare every single season with the exact same vigilance, regardless of what the macro-level forecast says.
Global averages are mathematically interesting to researchers, but they are entirely meaningless when local risk materializes over your roof. The ocean heat is there. The fuel is waiting.
This has been an incredibly deep, mechanically complex journey today. To synthesize the massive amount of ground we have covered, the ultimate truth defining this era of meteorology is a profound structural paradox.
A paradox we all have to live with now.
Artificial intelligence is absolutely changing the mathematical game. Deep learning models are bringing unprecedented computational speed, allowing us to see the probabilistic tails of the curve and predict catastrophic edge cases days earlier than ever before.
But the AI is not magic. It is just the digital processor. It possesses no inherent knowledge of the physical world.
It requires the entire massive physical ecosystem to function. It needs the low Earth orbit satellites, the daily weather balloons, the deep ocean buoys.
It requires the vital science of data assimilation, the highly specialized research scientists at OAR, and the irreplaceable human expertise to interpret the uninterpretable outputs.
The tension defining our lives and our safety right now is the brilliant, accelerating advancement of digital artificial intelligence, colliding violently with the slow, intentional decay of our public weather infrastructure.
And if we allow that physical infrastructure to decay, we render the brilliant algorithms blind, leaving ourselves profoundly vulnerable to the very storms the AI was built to predict.
Before we close out this episode, I want to leave you, the listener, with one final, highly provocative thought to mull over as you watch the skies this season. Something that builds directly on the research that has been done, looking just over the technological horizon.
The next immediate frontier of meteorological technology is moving far beyond passive, two-dimensional forecasting on a screen. Major multinational tech companies are currently utilizing vast amounts of capital to build generative, three-dimensional digital twins of the Earth.
A digital twin, what does that actually mean for the human forecaster?
We are talking about advanced AI systems that can generate a consistent, highly interactive, continuously evolving 3D simulation of the global atmosphere that inherently obeys the laws of fluid dynamics.
That sounds like science fiction.
In the very near future, a meteorologist might not sit at a desk and look at a flat, color-coded chart of mathematical probabilities. They might put on a spatial computing headset, physically walk inside a digital representation of a Category 5 hurricane before it even forms over the real ocean, look up at the eye wall, and visually watch exactly where the digital rain is going to fall on a specific neighborhood.
Walking inside a virtual hurricane to predict the real one, the computational scope of that is truly difficult to comprehend.
It's staggering.
But it raises a massive, pressing societal question. If the federal government intentionally defunds public weather research, if we shut down the data assimilation labs, ground the weather balloons, and allow the public observation networks to decay, and private, trillion-dollar multinational tech corporations take over the mantle of meteorological scientific discovery, what happens then?
That's the billion-dollar question.
What happens when the highly accurate predictive data that keeps your family safe from a rapidly intensifying hurricane, or tells a local farmer exactly when to plant their crops to avoid a freeze, is owned entirely by a private entity focused strictly on shareholder profit, rather than a public institution focused fundamentally on the common good?
It is a question of who ultimately owns the predictive future of our safety. And given the pace of the technology, it is a question we need to answer very, very quickly.
A lingering, vital thought for all of us as we navigate the incredible tension of this upcoming season. You've been listening to Meteorology Matters, created by meteorologist Rob Jones.
Stay safe out there.
Thanks for listening, and remember, meteorology always matters.